Hello, my name is John Matthews. I'm the Executive Director of Ingradata GmbH, a European software company specialized in Windows desktop applications for the process plant design industry. Ingradata was founded in 2012 as a spin-off from Autodesk Technology Corporation in Denver, Colorado, where I previously worked. We have over 30 years of experience in the process industry. Ingradata stands for Intelligent Graphics and Data, which describes how we combine graphics and data to create intelligent models. I'd like to tell you today about how we use the ODA Modeler technology to enhance our applications. Although we have our own rich graphics system based on Autodesk Series 5000 kernel, it's essential that we are able to exchange data with other systems, in particular the DWG format, which is a quasi-standard. For this, we rely on the DWG libraries, which we've been using since around 2008, when it was known as OpenDWG.
VectorPipe is the name of our 3D pipe modeling application. Its design is a multi-user concurrent engineering application. Projects are organized into groupings called assemblies, with access controlled at the assembly level via checkout and check-in. Virtually all project data is stored in the Oracle database, with graphics being generated on the fly. Orthographic drawings, isometric drawings, 3D model exports, and reports can be generated at any time on an as-needed basis. You might ask, why the name VectorPipe? It's because our product uses vector concepts for routing pipe. First, a point is chosen for the start of a pipe route. This can be a free point, in which case a direction must also be specified, or an open branch on an existing fitting, in which case the routing direction is automatically set by the branch vector. Next, a point is set along the current routing direction. For example, a point can be placed at a specified distance from the existing branch. The new point can also be specified using a number of other methods, such as with reference to other objects. The branch angle determines which way a change in direction will occur for components such as elbows and T's, or for valve spindle directions. In the branch angle dialog, we imagine riding on top of the pipe, looking along the direction vector and turning to the left, right, up, or down. For most components, VectorPipe uses a combination of simple solid shapes. For example, a pipe is constructed using a cylinder. An elbow is made using a torus section. A reducer uses a cone, and a foundation pad might use a box or wedge shape. More complex components use a combination of shapes. For example, a well-decked flange is comprised of a cylinder and a cone. And a pressure vessel might use a combination of a cylinder for the main body and half spheres for the top and bottom. A flanged valve with a hand wheel requires cylinders, cones, and a torus. In addition to generating orthographic and isometric drawings and bills of materials used for construction, VectorPipe produces various 3D export formats, including DWG and ASYS SAT. These can be useful in the project bidding stage to show the end customer the proposed construction, and also during the design phase for walkthrough and verification purposes. Recent development in the ODA Modeler technology provide better tools to reproduce the VectorPipe model in DWG and ASYS SAT formats. Most solid shapes used in VectorPipe can be directly generated into ODB 3D solid instances in the ODA. For example, a box, which might be used as a foundation slab, is made using the ODA Modeler function createBox. A sphere, which might be used in a valve body, uses createSphere. Cylinders for pipes and flanges and cones used in reducers are recreated using createFrustrum. Torus sections for making elbows can use the revolve function to revolve a circle about an axis. Similarly, a rounded tank top, which uses the VectorPipe primitive half sphere, is recreated by revolving an arc about the tank's central axis. and wedge shapes used for concrete support pads can be made using the extrude function to extrude a rectangle with a taper angle applied. Settings in the conversion utilities allow the component groupings and color scheme to be applied to the output. So if the coloring scheme in VectorPipe is changed to color by assembly class, we can obtain the same coloring in the output DWG. To generate the DWG, the components to be included are first selected. Settings in the conversion dialog allow the specification of the DWG and ACES versions. The export function then creates the DWG by translating each VectorPipe 3D shape to the equivalent DWG 3D solids. Here's an example. Here's another example. This is our PPD demo project with all the components loaded. And here you can see there are quite a few details there. Looks like all the components have come out correctly. Here's another one, which is a very large plant, and you can see lots and lots of detail there. And as we zoom in, you can see get right down to the tiniest valve.
Thanks for your attention. I hope you enjoyed the presentation. If you have any questions or would like some more information, feel free to email me at john.matthews@ingradata.com or come visit our website at www.ingradata.com. Thanks!